All right, let's talk a little bit about calculus and try and set the stage for the stuff that we're going to see later on when we figure out what the derivative is and talk about limits and all that other stuff. So what we're building up to, let's start there, and then we'll fill in some of the backgrounds that we've glossed over so far. So calculus fundamentally is the mathematics of change. We are asking about what happens to something as we change something else, right? That's sort of the quintessential calculus question. Now, as you go deeper into calculus, you start talking about things like integrals, where you are adding up change across a range of time. We're not going to get that deep in, but that stuff becomes important when you start thinking about the foundations of probability questions. So if you are interested in going down the route of hard fundamental work on probability, you definitely need to be getting that stuff. In any case, we're going to see these particular symbols a lot, and all of these symbols are basically some variation on delta. Delta is what we use as our symbol for change. Delta x, delta y, delta z, delta f, all of these mean the change in this thing. So these, well, there's a classic D, you know what that is. This we read as delta. This we read as partial, but it is also a delta. It's just shaped different because we use it in a different context. And then this capital delta, this is the lowercase, this is the uppercase, and this is just a distorted lowercase. So these three are all the Greek symbol delta, which is roughly the same as our letter D in our alphabet versus theirs, but they all mean change. So we're going to start at least wrapping our heads around the basic concepts by using physical analogies because it's just easier for our Paleolithic brains. So thinking about a change in position, we're fundamentally talking about velocity, right? Which is roughly the same thing as speed. Close enough for an economist. We'll talk about, in economic context, the change in value. So we've already seen a rate of return when we were talking about present value. We can talk about the rate of substitution as a change in value, and in that case, we're going to be talking about indifference curves, something that you might be seeing in intermediate micro already. And then change in productivity, also a big economic question. So we can talk about marginal product of labor, marginal product of this particular type of investment, right? If you are making a decision for your business, do we buy a new pizza oven for a pizzeria, or do we upgrade our server farm at Google, or whatever the question is? Marginal productivity questions come up a lot, which is the realm of calculus. And then the marginal rate of technical substitution, this is really the same thing as the marginal rate of substitution, just with an extra word in it. But here, instead of talking about utility, you're talking about productivity. So we're going to be building up the math to understand how this works, and you should feel already pretty okay with algebra, which is what we're going to be doing a lot of. So calculus is really just a step beyond algebra, at least as far as we're concerned in this class. So let's quickly fill in some technical details that we've encountered, but we haven't necessarily gotten bogged down in the terminology here. So we're thinking a lot about functions. And the way to think of a function is, I've got here two number lines, right? So you might have seen something like this. We've got 0 in the middle. As we move to the right, we're going to bigger numbers. We can go into the negative realm and look at smaller numbers. Here we've got some number line representing some x value, and we can ask, what's the domain of our function? We'll come back to that in a minute. And then we've got the function itself mapping this x value onto a new number line representing y, and the range of y is just the places where this function could end up, right? Now, our inputs, they might be something like integers if we're talking about how your children affect your annual or monthly budget. We could talk about real numbers if we're thinking about something like the numbers in your bank account or something continuous. But fundamentally, we've got just two number lines, and we take a number from one and we map it to another. Now, we could think of a function as fundamentally being a set of such numbers, right? So one possible set might be something like we take some number x and then we multiply it by itself, and that gives us y. So in this case, f of x is just x squared. So we take our x and we get y equals f of x. And the set of numbers that does that, we can think of algebraically, but we could also just think of it as, of all the many possible ways to map these different terms from x onto some y value, onto some y number line, if we just cut some of them out, right? We say those ones, those aren't part of this set. These ones, they are part of this set. So we could think of our function as fundamentally a set out of a very big set of possible functions. Now, the reason I bring this up is not because it's necessarily going to be directly useful for us for this class, but just as sort of a way of thinking about solving problems in general. I really like an analogy. I'm going to switch to my screen. There's an analogy from Stephen Wolfram, and I think we can find his book online, A New Kind of Science. Stephen Wolfram in this book is talking about computer science, and he's basically trying to build a theory of everything. And what he's saying, coming from the background of a physicist, is that the universe is fundamentally made up of computational processes. So our genes are code that take inputs and map those inputs to outputs. We as creatures are taking inputs from our environment, making decisions, and as a result ending up with a different environment. And the basic mathematics behind computer science are applicable there. Now, this is beyond what you and I need to think about as economists, but I think it's a useful metaphor, and particularly going into the middle of the 21st century, thinking about this idea of a large set of possible programs. We want to pull out the ones that work best, right? And not just work best, but work best in the environment of all the other programs that are running. So as a direct metaphor of that, we could think about, say, my computer, my literal computer. I want to be able to use R, and so it happens to work nicely for me to have access to the terminal, to the command line, and so it's nice to have a Unix-like system. It's also cool that I can do weird little things like this, which is nice. But more important, I've got this whole set of programs that work tolerably well together on my computer. That's the choice I've made. If I was a graphic designer, I would go with a Mac because I would want a different set of programs that work well together. If we think about the economy, a business model is very much like a computer program. So something like Walmart's business model of just-in-time delivery and doing an exceptionally good job managing a complex logistics chain, that is their comparative advantage. And that really boils down to a lot of literal computer programs, keeping track of their data, managing the delivery of stuff, managing their fleet of trucks, managing a bajillion different contracts from suppliers, all while anticipating the predictable but independent and complicated set of preferences of consumers. So that is one way that you could manage this whole sort of niche in the market. You could also have mom and pop stores that have a lot of stuff that sits on the shelf for years, never getting sold. And that's going to be a very costly way to do business, but it makes sense in different contexts, right? The economy is an evolutionary process, and it's easier to think about evolution when you're thinking about evolving processes, whether those are business processes, computer processes, or biological processes, there's sort of a very similar logic, which, coming back to here, is why I like to think about functions as these sets of mappings, these sets of arrows from x to y. And of course, later on, we can talk about more complicated functions. We can build functions out of functions, and that lets us think about, in sort of an abstract way, these more complicated processes that we see in the real world. All right, but let's come back to these sort of mathematical fundamentals. And actually, really quickly, I'll also say with set theory is very closely tied to the realm of logic. So the if then, the and, or, not, XOR, all those things we talked about at the beginning of the semester in the context of symbolic logic, a lot of those same processes work for here, right? So if we think about, we want a process that does something like this. We want a function that's going to do that. Maybe we are looking at data on people's wealth over time, and we want to try and predict what is someone's wealth going to be if they're 50 years old based on what their wealth was when they were 20 years old. So that's what we're doing in econometrics, where we're trying to build a function and match it to data. But if you're asking, well, what sorts of functions can we fit in there? What sorts of functions make sense? You could have something like y hat equals alpha plus beta x plus beta x squared. Let's call it beta 1, beta 2, and so on. You could have a function that looks like alpha times beta x to the power of beta x2, or whatever else. We could have infinite possible functions that we could use to model some process. But very often, especially in the case of econometrics, we are eliminating things based on what's going to work with our statistical expectations. We're going to tie it to some other area of mathematics. Or in this case, we want to model something that looks like it has compound growth, or something that actually compound growth would be a little bit different than this, but something that grows at an increasing rate. We can eliminate the mappings that have an upward slope, that go from a number to a smaller number. We can eliminate those that go to a larger number that isn't large enough if we're trying to model this. Right? So we can eliminate possibilities and narrow down our focus to particular types of functions. But that's sort of an abstract idea. Let's come back to the idea of domains and ranges. So a domain is the set of numbers that a function can take as input, and the range is the set of numbers that we can give as output. So if we're thinking about, say, supply and demand, we want to be talking about strictly positive quantities of some good. You can't have negative beers. We could talk about negative values if we're thinking about futures markets, but let's not get there. Let's just simplify and say you can only have positive values of goods. We would be looking at a specific domain. Let's look a little bit more abstractly at this function in particular. F of x is the square root of x squared minus 1. So if we put in, say, x equals 4, then f of x equals the square root of 4 squared minus 1 is the square root of 15, which is a real number. If we say x is 1, then f of x equals the square root of 1 squared minus 1, which is just 0. All right, 0 is a real number. If we put in 0, now we've got the square root of minus 1, which there is such a thing, right? We could have an imaginary number representing that. And this is sort of what mathematicians are doing, is they're coming up with, well, have been over a very long time, coming up with new ways to model something, right? New logical systems. But in economics, we're never going to be using this, certainly not in this class. So given that, we can say, all right, this is not a real number, right? It's an imaginary number. Real numbers are not allowing for a negative square root. So, since we can't have a contract that says, you owe $50 plus 3/2 I, we don't have contracts in imaginary terms, so we just say that is not something that we're going to consider. We're going to say in real terms, this function is not defined right there. Doesn't fit. Doesn't make sense to say 0. Doesn't make sense to say anything between 1 and -1. So if we go to, let's say, -2, just to verify, -2 squared minus 1 is 4 minus 1 is 3, is the square root of 3. So we have a way to turn this into a real number, right? Now, if we were restricting ourselves to integers, that wouldn't work. If we were looking at rational numbers, that wouldn't work, but it's a real number, right? So it's going to do well enough for us. Now, very brief aside, right? You guys are probably familiar with integers and real numbers. 1, 2, 3, the whole numbers are integers. 1.5 or pi, these are real numbers. There are some real numbers that we call rational and some that we call irrational. A over b, this is rational because we can make it as a ratio. Pi is irrational because the only way we can express pi as a fraction is pi over 1. We can approximate pi, I think it's 22 over 7. So 22 over 7 is a rational number, but the actual number we want, 3.1415, whatever the rest is not reducible to a fraction. So it is an irrational number. You don't really need to know that for this class, but it's just a cool little, out your window on the left, you will see moment. There's a lot of cool stuff in math that we don't need to know, but still nice to see. So, given this, right, we've got, in this case, all these possible real numbers that we might think about putting into here, but it's undefined on this portion. And its domain is everything else. Essentially what we're saying is if a number is a domain. So we can ask, is domain some number x? Is it going to be in the domain? Well, if the number is between -1 and 1, it's not in there. So if the absolute value of x is greater than 1, right? So greater than or equal to 1. So 1 has an absolute value of 1. -1 has an absolute value of +1. -1.5, the absolute value is greater than 1. Therefore, that would be in the domain, right? We could ask, is it not in the domain? And we could use a little bit of our logic from earlier on and just say, is it not this, right? Just the negation of that. So the domain is the numbers that we are allowed to use with this. And that maps from x into some range, which is some set of possible numbers that this particular function can work with, or any particular function. Now, let's talk about 2 more things, and then we'll take a little break. So first off, composing functions. So just as we can take x and map it to y, we can take y and map it to z. Right? We can take one number, or for that matter, we could take numbers from multiple domains and map them onto one range, which is, again, another thing that you might be doing in econometrics. But let's not worry about that right now. Let's just think about, we take some function, right, some mapping from x to y, and we can put that into some other mapping. Now, this is going to come up when we talk about the chain rule. So what we're doing is we're chaining together two functions. So we're saying we've got f of x, and then we've got, say, g of y, but really g of y is g of f of x, right? So we've chained together this function, or put another way, we've composed a more complicated function than what we started with. Right, so that's one way we could do it. We could also do things like, say, f of x plus g of x, right? That's another possibility, right? So there we're essentially saying we've got x, and we get f of x, and we get a g of x. Whoops, lost the screen. We're getting two numbers out of that, and then we're putting those together into some final thing. Let's call it h of x equals f of x plus g of x, right? So here, if we're wanting to understand the function, right, and again, going back to what we're talking about, we're thinking about how is the value of this function going to change as we change x. In that case, we're going to need to trace back through both of these branches of the function. So that's a composition of the function. Now let me break from this kind of funny notation I've been doing. So I've been doing, here is x, here is y, and I've got these connections between them because, well, I just like this visualization. I think it does a nicer job of explaining what's going on. But we're going to do what's more traditional. We're going to take this x-axis and we're going to flip it horizontal, and we're going to superimpose these two number lines over each other at a diagonal, or orthogonal to each other, right? So we're going to have x crossing y instead of being in the same direction. It's going to be the same fundamental thing, but now what we're saying is, let's say 1, 2, and 3, 1, 2, and 3, we were mapping to, let's say, 1, 4, and 9. So now we're going to have 1, 4, and 9. So we can represent f of x now as this line in two dimensions. This is the Cartesian plane, or two-dimensional space. So we're going to be using this a lot. We've already been using this a lot. But again, here's a point where our set theory thinking helps, right? So with a set, all we're thinking is Venn diagrams, right? We're thinking about, say, all the possible functions, and then all the possible functions that map a number to a positive number. And then we cut out some other stuff until, finally we find this one part that overlaps everything we care about. And our function is one of a bunch of functions in there, right? We're eliminating possibilities. Now, in this case, what we're saying is each of these points, right? So you've got 1, 1. We've got 2, 4. We've got 1.5 and f of 1.5. That's a little bit messy. Let me make this bigger. 1.5 and whatever 1.5 squared is, right? Each of these points, we've got infinite points all through this blue line, and that is a set of outcomes, right? Fundamentally, any line that we draw or any blob that we draw, right? So if we draw, say, something like a budget constraint, we can represent this with an inequality. We can say budget is greater than or equal to the price of x times the amount of x we buy, plus the price of y times the amount of y we buy. And we can rearrange this appropriately to do whatever we need to do, right? Change it to fit the problem we're trying to solve at any given point. This is a set of many, many, many possible points. Right? Now we're using real numbers here, so technically we have infinite possibilities, but this is including the possibility that you go to Dunkin' Donuts and you buy 11.375 donuts, which isn't practical, but the math is easier, right? So sometimes we have situations like that. This is a set of possible consumption points, and this blue line is also a set of points. It's a skinnier set stretched across a very long space, I guess technically an infinite space, but it is still fundamentally a set of outcomes, right? So think of this line that you drew as similar to this triangle you shaded in. This is the set of combinations of x and y that match with this function, that satisfy the definition of this function. All right, so that was some abstract stuff, which is going to take some time to settle in, but keep this in the back of your heads. This is stuff that we normally would spend a lot more time in class discussing, but in practice, especially as economists, we don't really use it that much. But nonetheless, it helps to sort of look under the hood of the math that we are using. Understanding how the math works is going to make it easier for us to make good use of that math.